Hello, everyone, and welcome to the Great Lakes Biochar Network's second seminar here in the fall of 2021. This one is on the production of biochar. We're going to give it a few minutes as people trickle in. I see that number of participants going up right now. If you wanted to introduce yourself in the chat, just your name and where you are, feel free to do that. And then we'll get an idea of where everyone is coming from. If you wanted to say if you are also currently producing biochar, that would be some interesting information, or if you're just here to learn more, that is wonderful also. So again, we're going to wait a few more minutes as more people come on to the webinar, and we will get started in a few minutes. All right, another person from Lansing, welcome. Again, if you want to introduce yourself in the chat, a little bit of housekeeping also is that we will be having a question and answer session. This is the presentation by Dr. Christopher Saffron from MSU's Biosystems and Agricultural Engineering Department. And the presentation is going to be about 45 minutes. And then at the end, we will have the Q&A with him live and other people from the Great Lakes Biochar Network and able to answer any of those questions. If your questions don't get answered, then we will certainly try to address them at a later date, but hopefully you will be able to talk about all of those that get presented today. So keep those coming throughout the presentation. They might even get answered in real time being typed into that Q&A forum. Otherwise, they will be answered by Dr. Saffron after the main part of the presentation. It's great to see some people that are producing as well coming in there in the chat. You know, as also we go over things, one thing that will be interesting to hear is what other types of webinars, and we're always open now as this newly formed network where the network really is everyone. It's the core group that had started at MSU, but we want to be involving everyone. So let us know what other types of webinars you might want in the future. And in terms of production, we might even have a panel of producers on in the future as we look into 2022 and further of connecting people and everything else within the biochar bioeconomy here in the Great Lakes region. See, we're up at close to 50 people right now. Please do keep introducing yourselves in the chat if you're just coming on. But I am going to get started. This is the Great Lakes Biochar Network, and we are talking today about the production of biochar. I am Dr. Brooke Comer. I am the program coordinator for the Great Lakes Biochar Network. So you are probably hearing any communications are going to be coming from me, and I am always here and open to all of the practitioners that are involved in biochar to get in touch with us and figure out how best we'll all be connecting. But the webinar today is led by Dr. Chris Saffron from MSU Biosystems and Agricultural Engineering, and also with support from his graduate student PhD candidate, Rachel Sack, also in Biosystems and Agricultural Engineering. And he is going to introduce himself a little bit more. Again, throughout the presentation, feel free to use the Q&A and also the chat if you want to be talking to other participants also. I will say, well, actually going back here, I do want to say that our funders here are MSU Project Green, the Michigan Department of Natural Resources, Division of Forest Resources. This was through a 2019 landscape scale restoration grant from the USDA Forest Service and support from MSU Extension. And this combined with all these webinars and just starting off here in 2021 is really the start of this network, which originated here at Michigan State University, but it will be powered by and made up of people throughout the region. And so we're here to help connect participants and stakeholders from all across the Great Lakes region and even beyond. And that will really embody the network. So the goal to serve the entire region and all interest regarding biochar. notice of non-discrimination. The Michigan Department of Natural Resources, MSU, and the USDA were all equal opportunity providers and are prohibited from discriminating on the basis of race, color, national origin, sex, or disability. Also, this is going to be recorded. Our goal is to provide the record of the webinar posted on the website, which will be providing that link later. And also we'll have an ADA compliant PDF of the slides. In addition, any suggestions on how to make our offerings more inclusive and more accessible, please contact me with those suggestions. And with that, I am going to send this over to Dr. Chris Saffron. And that will be starting now. Thank you so much for being here.
Welcome to the Great Lake Biochar Network's presentation on biochar production technologies. My name is Chris Saffron. I'm an associate professor in the Department of Biosystems and Agricultural Engineering. I also have adjunct appointments in forestry and chemical engineering and material science. My colleague, Mrs. Rachel Sack, is a PhD student in the Department of Biosystems and Agricultural Engineering. And we're going to tell you about some of the reactor configurations that are used to make biochar. And so the first question is, what is biochar? Biochar is a product made from the pyrolysis of biomass. And biomass can take a number of different forms. It can be woody biomass, perhaps woody biomass grown in plantations. It can be forestry residues, sawmill residues, agricultural residues like corn stover, animal waste like some of the dry manures, horse manure, for example, as well as aquatic biomass, perhaps macroalgae, the seaweeds after they've been dried. And from there, we heat those biomass forms in the absence of oxygen, and this is what's very important here. If we let in too much oxygen, we'll combust all of the biomass to CO2 and water vapor, and we won't get very much biochar or very much bio-oil if the liquid is what we desire. The temperature range that we are most interested in typically occurs between 300 and 700 degrees Celsius. Perhaps an even more narrow range of 400 to 600 degrees Celsius is even more typical. And the products that we produce include a solid, which we refer to as biochar, a liquid, which is now called bio-oil, and a combustible gas. And we often combust that gas to provide some of the drying heat and some of the ignition heat that's needed to get the pyrolysis reaction started. We'll use the words biochar and char synonymously in this particular presentation. Charcoal can also be made from biochar and often is, though charcoal typically has other additives, sometimes including coal itself, hence charcoal, and sometimes including binding agents like starch. And this is how char briquettes are held together often, is by adding some starch. But what we're talking about will be biochar, where our end use applications will be such things as soil amendments or as sources of energy for heat and power production. So biochar is made by a number of thermochemical conversion technologies. At the low temperature end is the technology known as torrefaction. The chemistry of pyrolysis does start to occur during these temperatures, during torrefaction. And you can see the top figure on the left-hand side under the word torrefaction. You can see slightly toasted wood to heavily roasted wood, depending on the torrefaction severity in terms of time or reaction time or temperature of the reaction. Below that figure is pelleted torrefied biomass, sometimes referred to as char or biochar. That pelletized torrefied biomass would be used to displace a solid fuel at coal burning power plants. As we move up this temperature range into the 400 to 600 degrees C range of temperatures, this is where the technologies of pyrolysis are employed. And they can be employed as either fast pyrolysis, which rapidly heats biomass in the absence of oxygen, or slow pyrolysis, which much more slowly heats biomass in the absence of oxygen for much longer residence times. Fast pyrolysis residence times are on the order of seconds or less. Slow pyrolysis residence times can be minutes to hours to days. And you can see the types of charred products that we make. If you focus on slow pyrolysis, which is the dominant focus of today's talk because the char yields are so high during slow pyrolysis, we can do a number of things. We can make briquettes like you see in the picture in the middle, bottom right, or we can use the char as a soil amendment. And in use as a soil amendment, we may see things like yield enhancements of crops. And so here we show you a diagram, a picture of two plants growing, one in soils that include biochar and one that doesn't. And you can see the plant on the right has grown to higher yields. And so this is often what one wants to observe when they amend their soils with char. You can also make biochar by gasification. Gasification's goal is to produce gas, and then there's a number of different things we can do with that gas. We can burn it directly for heat and power, or we can upgrade it into liquid fuels using Fischer-Tropsch synthesis. It also co-produces a small amount of char or biochar, and that small amount of char could also be used for various purposes. I'll point out that when you get to higher and higher temperatures, the possibility of making polyaromatic hydrocarbons and some other organic contaminants does increase. And so this is something to be wary of when it comes to using these gasification chars. Not always the case, but sometimes it can be the case. So focusing on pyrolysis, this begs the question, how does pyrolysis occur? And the truth is the mechanism is very sophisticated. Pyrolysis reaction chemistries are quite complex. There's a number of different reaction pathways that are followed from the carbohydrate polymers of biomass, including cellulose and hemicellulose, as well as the lignin component of plant biomass. Fred Schaff-Izeda proposed a model some time ago in the late 70s, early 80s that describes wood pyrolysis. And he suggested that pyrolysis proceeds via three routes. One route to the char, which is our interest here today, another route to tar, which is now named bio-oil, and a third route to combustible gases. And these combustible gases are sometimes coined non-condensable gases. This is the gases left over after you've condensed the pyrolysis vapor to form the bio-oil. And then there are routes from the bio-oil to the combustible gases and to the char as well. And so there are secondary routes that can produce more biochar and more combustible volatiles. So this mechanism was kind of useful because it helped us to try to untangle what might be happening during pyrolysis mechanistically. Though today we've made rapid strides forward in our understanding of pyrolysis, we do have a ways to go. We care about these sorts of mechanisms because if we know the kinetics, we know the rates at which reactions occur, we can use that information to better design our reactors. Now we couple these rate equations that we can formulate from the kinetic models with heat transfer rates and mass transport rates. And so when we do that, we can better understand the entire physical chemical process of pyrolysis. And so when you heat a thermally thick particle, perhaps with a radius of 20 millimeters or more, like the spherical particle you see on the left-hand side of this slide, as you heat it externally, you get an expanding layer of char that forms, that surrounds a rapidly decreasing unreacted core of biomass. And as that biomass core reacts, it forms pyrolysis vapors and more char. The pyrolysis vapors then have to transfer across that char layer in order to eventually vent out into the space in between these char particles. That's the pyrolysis vapor that we collect and can condense to make bio-oil. It's important that we understand these mechanisms, particularly the rates at which these vapors are going through this char layer, because embedded in that char layer are the metals that the plant had transported from the soil. And some of these metals are actually quite catalytic and can catalyze a number of other reactions that then proceed to form products that are collected in your pyrolysis vapor. Or they can catalyze the formation of chars. And so understanding what's going on is really important because now we can design better reactors using that understanding. It helps us to de-risk reactor design. On the right-hand side is a similar model, only now the particle size has been reduced to 0.05 to 0.5 millimeters in radius. And this particular model proposed by Jansi and et al. Suggests that because of the transpiration tissue, the vessel elements and tracheids and so forth that made up the conduits from roots through shoots to leaves for water flow, because of the directionality of that transpiration tissue, the formation of pyrolysis vapors also proceeds unidirectionally through these particles. And so this is actually a somewhat interesting finding, because now you can determine what the residence time of these vapors happens to be inside these particles doing pyrolysis. And this leads to one reason why you might elect to use fast pyrolysis versus slow pyrolysis if your aim is to make liquids. There's a smaller amount of time in which those cracking reactions involving the metal catalysts embedded in the char, there's a very small amount of time that those cracking reactions can occur if you have very small particles. And so results like that are important because, again, they inform our ability to design better reactors. Well, there's a lot of mathematics and a lot of chemistry that really accompanies this, and it takes quite a deep dive to really understand what's going on during the slow pyrolysis process as well as the fast pyrolysis process. Now, it turns out it's actually quite easy to perform pyrolysis. Here is an example of an earthen pit kiln. And in an earthen pit kiln, you can see that we let air in on the far right-hand side. I'll point to it, the laser pointer. Air comes in, and this is a small amount of air. This isn't enough air to completely combust all the feedstock that we've buried in this earthen pit kiln. And what that does is it combusts a small fraction of that feedstock. Combustion is an exothermic reaction, so it generates heat. And that heat then is transferred to neighboring logs of wood to convert that material into biochar. And so once these reactions of pyrolysis are ignited by combustion, then they are self-sustaining. And what happens is the vapors that are formed pass through and come out over here on the left and are emitted into the atmosphere. I'll point out these earthen pit kilns are covered with soil, usually sandy or loamy soil. And it's important to make sure that as this kiln operates, recognizing that the biochar volume reduces, it's important to fill in any cracks or fissures that form, because those cracks and fissures will allow fresh air to infiltrate and cause combustion to occur. And so this isn't something that can be done for 20 to 30 days without monitoring. It does take frequent monitoring to make sure that anoxic conditions those are conditions in the absence of oxygen. Anoxic conditions are held. This type of kiln system prefers a well-drained soil. You certainly don't want a lot of water down here. Okay, and so that's important. Char yields are quite variable using this type of system, from as low as 12.5% weight on biomass to as high as 30 weight %. There's really no automated temperature control here. And of concern that we'll talk about in a subsequent slide happens to be the emission of particulate matter as well as volatile organic compounds. And so if you're going to perform earthen pit kiln pyrolysis, be aware that those emissions are occurring, and that if you have neighbors nearby, there may be some nuisance odor complaints. Okay, so if the soil is wet, or if it's just difficult to move, it's difficult to dig into, you can essentially perform the same type of pyrolysis in a mound kiln. And so this is just an above ground kiln, and we show you a depiction of that here. In the mound kiln, we typically leave a number of air inlets down below, and those air inlets can be plugged once the pyrolysis is ignited and slow pyrolysis is occurring. Char yields from these mound kilns tends to be in the 2 to 42% range. This is actually quite a broad range, but mound kilns are inexpensive to build. Here's a mound kiln where they've actually connected multiple 55-gallon drums to serve as a chimney. And so that's one way of lifting these emissions sort of off the ground. And so perhaps nearby neighbors won't be exposed to any of the problematic molecules that you're emitting during pyrolysis. We'll talk more about those in a moment. This particular mound kiln does have a condensate pipe to collect liquids. So liquids that condense from the vapor can be collected there. And those liquids can be burned as a source of heat or power if you have a heat and power generator. You can also perform slow pyrolysis in a batch drum. This is a batch drum kiln. This is just a 55-gallon barrel. This system costs about $15 to make, and this company, Biochar, has made thousands of these and sold them in the US and Kenya. You can get temperatures around 500 degrees C under low oxygen conditions and make biochar, in this case, for the purpose of its use as a soil amendment to improve crop yield. More sophisticated reactors have also been devised. This is a multiple hearth kiln. This particular kiln can operate at up to 2.75 tons per hour. And the feed comes in up at the top, and it goes into the first tray you see here. And these are what are called rabble arms. These rabble arms are connected to a center shaft, which rotates. And as the central shaft rotates, the rabble arms push the biochar towards holes in these trays, allowing the biochar that's forming biomass on the top tray, but eventually biochar, as you get to lower trays, pushes that solid material to a lower tray. And this material, your feedstock, is successfully pushed to lower and lower trays, exposed to temperatures of pyrolysis. Pyrolysis occurs, and by the time you get to the bottom, you can collect your biochar product, listed here as charcoal. Okay, but it would be biochar when you start with biomass. Going into this multiple hearth kiln in a countercurrent direction, we let in some air. And so this air then combusts a fraction of the biochar. And it's that combustion that generates the hot gas that raises the temperature into the 400 to 600 degrees C temperature regime that causes the pyrolysis to occur. And you can see here we can collect the particulate emissions, collect the volatile organic compounds that come off. And in a system like this, we could design an appropriate flare such that we convert those carbonaceous emissions into CO2 and water. You could also splice in between the flare different types of pollution abatement equipment to minimize emissions. This is called a multiple hearth kiln. Cornell has devised a reactor, a continuous reactor. And this continuous reactor is of the drum kiln variety. This particular reactor exists in one of their pilot facilities. It can accept up to 50 kilograms per hour of throughput. There are 5 adjustable heating zones, and you can achieve temperatures up to about 600 degrees C. There's a variable in-feed agitator, and that agitator is connected to a number of paddles, and those paddles push the biomass through the barrel. You can control residence time with the variable speed drive on that series of rotating paddles. You can also increase or decrease the inclination angle of the drum kiln, which also assists in controlling and adjusting residence time. And so they can control residence times between a low of 9 minutes to 45 minutes in this particular drum kiln. So there's some control of residence time, which is one of the key operating variables, and there's control of the temperature, another key operating variable, as well as the feedstock flow rate. And so these types of reactors are highly instrumented, highly controlled, and because of that, you can achieve biochars with more desirable properties than you might otherwise be able to. There are also fast pyrolysis technologies, and I just share with you two. The one on the left is a fluidized bed reactor, and in this fluidized bed reactor, the biomass is metered into a sand bed, which is fluidized by hot gas from underneath. And the hot gas imparts a force on the sand particles that are in this fluidized bed that counteracts exactly the force of gravity in the opposite direction. And so this sand doesn't move, but it is gently fluidized, which allows you to push the biomass into the bottom side of the reactor. The sand serves as a heat transfer medium, rapidly transferring heat to biomass in the order of perhaps 1,000 degrees Celsius per second. And what happens is you create pyrolysis vapor and biochar. Those become entrained in the upward flowing gas, and they go into a cyclone where the char and pyrolysis vapors are separated from one another. The pyrolysis vapors are then condensed to form bio-oil, which is the liquid fuel intermediate to hydrocarbon fuels, and then biochar. You typically don't get the same yields of biochar with fast pyrolysis as you do slow pyrolysis, on the order of 15 to 20 weight% for fast pyrolysis, whereas you can get 35 to 40 weight% biochar yields with slow pyrolysis. Nevertheless, if liquid fuels are needed, and if liquid fuel economics from fast pyrolysis systems can be supported, biochars could be produced in relative abundance because of the magnitude of the demand for liquid fuels. The reactor on the right is a recirculating fluidized bed. And I just want to point out a number of the fast pyrolysis reactors don't actually produce biochar. They don't export biochar. They produce it, but they don't export it. And so what that means is the char comes out with the sand, which in the case of a recirculating fluidized bed comes overhead with the gas and char. And then the char and sand go to a char combustion unit where the char is combusted in the presence of the sand to reheat the sand. And then the sand is augered back into the reactor. And so char doesn't get exported from the battery limits of the pyrolysis facility. And so not all fast pyrolysis technologies actually sell biochar as a product. What we have at Michigan State is something in between fast and slow pyrolysis. Our residence time is on the order of 20 to 30 seconds. This is a screw conveyor pyrolysis reactor. And up here at 4 is our feed hopper. And the biomass goes into our feed hopper and then down into the reactor barrel. We have 3 heating zones here, and we can control our temperatures up to about 550 degrees Celsius. And what comes out of the reactor is biochar and pyrolysis vapor. We don't use sand as a heat transfer medium. Instead, we use the externally heated wall of our reactor as the source of heat transfer. The vapors are then condensed through 2 condensers, and recognizing that even after condensation, we have aerosols in our gas stream, we run the stream through an electrostatic precipitator, which strips the remaining aerosols. And from there, the gases come out and go into a flame calorimeter where they heat water, a known quantity of water, and then we can record the temperature rise to calculate how much energy the gas stream has, recognizing that we would want to use that gas stream as a source of heat to heat our reactor. And here's a picture of that reactor setup. And so you can see the feed hopper here on the left, the reactor barrel on the bottom. This is the char trap and the 2 condensers. We collect our bio-oils in ball mason jars. This gas then goes overhead to a electrostatic precipitator, and then below this electrostatic precipitator is another ball mason jar. This gas then goes over into a flame calorimeter, and we can measure the energy content with that device. Looking down the biochar trap, if we take the top off, you can see that we collect biochar there, and we typically get yields, well, as low as 12 weight%, and as high as 25 weight% in this particular device. And the non-condensed gas is combustible, as you can see here. So just in review, starting with torrefaction, this is the low temperature version of pyrolysis. We do get at relatively high solids content. That material is really for displacing coal at coal-fired power plants. Though you get a high solids yield, there's still a lot of unreacted biomass in torrefied biomass, the torrefied biomass product that you produce. And that unreacted biomass would include things like carbohydrate polymers, cellulose and hemicellulose. And so often we don't consider torrefied biomass as a source of biochar for soils. Instead, we look to fast pyrolysis and slow pyrolysis for doing that. Fast pyrolysis biochar yields are about 15 weight% or so. Slow pyrolysis biochar yields are about 35 weight% or so. Yes, you can derive biomass from gasification in the order of 10%, but we just have to be a little careful as to what sorts of organic contaminants that biochar might contain because of the high reaction temperatures we exposed that solid material to. There are a number of biochar applications that we need to be aware of that go beyond its agriculture use. Of course, heat and power is one use. We could burn biochar, make heat and power. There are a number of future uses that involve the building sector, and this owes to biochar's low thermal conductivity, its low flammability, its high stability. We can use biochar as a catalyst. We use it as an electrocatalyst in some of the electrocatalysis work we do to upgrade pyrolysis biooils. There is some evidence that it serves to replace sulfuric acid in biodiesel production. Animal feed additives is another area of application. There's evidence of increased gut health, increased feed efficiency, toxin absorption, as well as decreased methane release, very important for the cattle industry. There are human healthcare applications that can be expanded upon with biochars, and then some more unique applications like sodium-ion battery production, where amorphous carbons are needed, or the production of supercapacitors. And so there's lots of different directions biochar is going with regard to end uses for it. A number of folks have wondered about different activation techniques. Classically, biochar is activated most often by steam, where the steam is usually high pressure, high temperature steam. And what this serves to do typically is to increase the surface area of these biochars to make activated biochars or activated carbon. And having activated carbon is important because it'll increase the adsorption and removal of such contaminants as heavy metals or dyes or oils from water streams or from air streams. Very important for wastewater treatment. And so classical activation involves perhaps steam or other gases like carbon dioxide can be used as an activating agent as well. And there are a number of other methods, physical methods used for activating biochars. It's not just about increasing surface area, however. Changing the functional groups on the surface of biochar can also be desired. For example, you might elect to increase the cation exchange capacity by oxidizing the surface of biochar using hydrogen peroxide, in which case you're using a chemical activation approach. And there are a plethora of chemical activation approaches that involve acids and bases and so forth, where the goal is to change the types of functional groups, to add functional groups, to subtract functional groups from the surface of biochar. And lots of end uses for these sorts of things, from electrochemical energy storage to pesticide removal. It can improve biochar as a soil amendment, for example, if you increase the cation exchange capacity. There are biological activation mechanisms used as well. Composting is an example. You just mix the biochar into a compost pile for weeks to months, and what you end up with is a biochar that can improve soil structure, soil properties. You get some increased water availability, some evidence of decreasing nitrous oxide and methane emissions from field applications. And so there are biological activation methods that are of interest to those of us in this field as well. So even from the same feedstock, biochars produced under different operating conditions will be different. And so here's a study by Brun et al. Published in Soil Biology and Biochemistry using wheat straw as a feedstock. And they examined 4 treatments: a soil control, where they didn't add biochar, and then a treatment that adds slow pyrolysis biochar at 5 weight % in soil, another treatment that adds fast pyrolysis biochar at 5 weight % in soil, and then a final treatment that just takes raw, untreated wheat straw and adds it in 5 weight % concentrations in the soil. And so the slow pyrolysis biochar was produced under different conditions than the fast pyrolysis biochar. The heating rate was much slower at 6 degrees Celsius per minute versus 250 to 1,000 degrees Celsius per second. And the heating time was 2 hours for slow pyrolysis versus less than 3 seconds for fast pyrolysis. And so then they went through and they looked at some of the properties of these different biochars and compared them. And so looking at the carbon content, you can see the slow pyrolysis biochar has about a 78% carbon content, whereas the fast pyrolysis biochar is at 49%, only slightly higher than the untreated straw. The oxygen contents are also very different. The slow pyrolysis oxygen content is about 7%, and the fast pyrolysis oxygen content is 24%, both substantially lower than the 44% oxygen content of the original straw, wheat straw. The ash fractions are about 20% for slow pyrolysis and almost 22% for fast pyrolysis. So they're not too different, but they are quite different from the original wheat straw. And that's because the biochar concentrates the inorganic component, the inorganic fraction of wheat straw into itself. The inorganics typically aren't volatile, so during pyrolysis, they just become a fraction of the biochar. Cellulose and hemicellulose does remain. There's a small amount of these carbohydrate polymers present in the fast pyrolysis biochar, but none of them present in the slow pyrolysis biochar. The pHs are different. The pH of slow pyrolysis biochar is relatively high at 10.1 and about neutral for fast pyrolysis is 6.8. And interestingly, the surface areas aren't that high. We tend to think of chars, biochars as having high surface area, but these surface areas are actually quite low from both of these two processes. These surface areas are quite a bit lower than wood char pyrolysis, particularly as those are around 100 meters squared per gram. And so something's different about wheat straw than would be biochars made from woods. Now, if you employ steam activation, one of the physical processes we talked about, you can greatly increase these values. Well, this difference in properties has some ramifications. This experiment that was conducted observed that there was a CO2 pulse from the different soils that were collected during the first 10 days of a 65-day trial. And the pulse was found to be greatest if you just land applied the wheat straw. The wheat straw was very accessible, very labile to the microorganisms in the soil. And so you've got a large CO2 pulse as a result. The slow pyrolysis pulse did occur, but it was very small. And the authors attributed this perhaps to some adsorbed CO2 on the surface of the biochar owing to its high pH. Bases are capable of trapping acids. CO2 is an acid. When it's dissolved in water, it forms carbonic acid. And so perhaps some of that CO2 is trapped on the surface and was just liberated over the course of the first 10 days. Fast pyrolysis pulse was greater than the slow pyrolysis pulse, and they attributed this to the fact that the fast pyrolysis had a larger content of these carbohydrate polymers, which microorganisms perhaps were able to access quite easily. And then, of course, the microbial mineralization rate from wheat straw was quite large. Well, this slide just serves to impress upon you that biochars, even from the same feedstock, have different properties when land applied. And that owes, at least in part, to the physical chemical properties of the biochars as made by these different processes. Air emissions are important to discuss. Recognize that fast pyrolysis air emissions will be different than slow pyrolysis air emissions. There are lots of organic constituents in both slow and fast pyrolysis emissions. I will say that the slow pyrolysis vapors tend to have higher contents of carbon oxides like carbon monoxide and carbon dioxide. So just considering the slow pyrolysis air emissions, in an uncontrolled batch reactor, you can see the emissions in terms of carbon monoxide, in terms of methane, in terms of non-methane hydrocarbons and total suspended solids are greater than if you work with a controlled continuous reactor. The controlled continuous reactor emissions are quite a bit lower. And so your ability to control those emissions goes up with increasing automation. That's something to consider when it comes to regulating emissions and considering whether to practice at small scales or large scales. The energy analysis of pyrolysis is also interesting. If we take corn stover, which is the leftover stalk and leaves of the corn plant after grain harvesting, and we take 1 metric ton and we push it through this process of drying and pyrolysis. You can see of the 16,000 megajoules that goes in, more than half comes out as biochar under slow pyrolysis conditions. And the rest goes with the vapor stream, which this group has elected to oxidize thermally, combust, to generate a hot gas, which is then run through a heat exchanger to transfer the heat and deliver it to heat applications, which include to some extent the processes of drying and pyrolysis themselves. You can see these recycled heat lines here. Note, the amount of process heat needed for pyrolysis is not that great. You have to add some energy to raise the temperature, the specific energy needed to raise the temperature to the ignition temperature of pyrolysis. But once it gets started, it's fairly self-sustaining, so it's not very energy intensive to run. What they learned in this study was that dry feeds like poultry manure, horse manure, or dry cattle manures are actually reasonable feedstocks for this type of system, but wet feeds like dairy manure aren't, and that is because of the need to boil water off the wet feed prior to performing pyrolysis. They also learned that yard waste was a very economically favorable feedstock because you can charge a tipping fee, and they learned that carbon credits are important. When they got to carbon credits of amounting to $80 per ton of CO2 equivalent, that led to economic feasibility. And they also found that the economics were favored for decentralized distributed systems, smaller systems, perhaps cooperatives, farmer forest cooperatives, where these systems are located near to the feedstock. So the hauling costs are minimized. Different researchers have looked at centralized facilities. This is an example of a large centralized facility processing 2,000 tons per day of dry corn stover. And they used slow pyrolysis at 400 degrees Celsius in 1 atmosphere to achieve an internal rate of return of 10%. To get that internal rate of 10%, they needed a biochar selling price of $346 per metric ton. You'll see in a subsequent slide that selling price of biochar is very important. At $60 per metric ton CO2 equivalent, this equates to about $110 per ton of biochar. So that gives you an idea as to what carbon credit and what additional value biochar has to have in order for it to be accessible on the market. And they have performed this sensitivity analysis and recognized that biochar yield is a very sensitive parameter. And here you can see that if you increase the biochar yield from 36%, which corresponds to their 10% IRR down the center line, you increase that to 45%, their IRR approaches 20%. If the biomass cost is decreased to $55 a ton from $83 a ton, then they also start to approach 20% IRR. If you can get a gas credit from the co-produced combustible gas, you can get IRRs of 20%. Fixed capital investment, if it's lowered from $113 million to $79 million, this also increases your IRR. And so you can see from this tornado sensitivity plot what variables most sensitively impact profitability. And what we learn is that IRR must be high to attract bank investment, and 10% might not be enough to do that. Another study came along and looked at biochar selling price. And so they surveyed biochar selling prices back in 2013, and they learned from that survey that the prices range from $80 to $13,480 per metric ton. This is a very wide range of prices. At least in part, it owes to biochar properties. Okay, the properties are different, and so the prices, the value of the material is different. And what this group did is they looked at 4 scenarios using 2 different reactor schemes. Scenarios A, B, and C all used an auger reactor. And scenario D used a hearth kiln reactor. Scenario A co-produced biochar and liquid fuels, but didn't include RIN credits. And so by not including RIN credits, you can see their net present value tends to be below 0, all right? So these distributions that are plotted here are plotted by performing a Monte Carlo simulation where they did 10,000 iterations with varied parameter sets, where each parameter was varied within its own distribution function. And so upon going through all those iterations, they were then able to determine the distribution of net present values that could be achieved for each of these scenarios. Because scenario A's mean net present value is negative, more likely than not, this auger production technology using RINs wouldn't be feasible under the conditions of fuel prices imposed in 2018. We had low fuel prices in 2018. You go to figure B, you can see with auger production, including a RIN credit, this shifts the distribution over where the mean distribution is now right at about a net present value of 0. If you only produce biochar in an auger, okay, without a RIN credit because you're not selling liquid fuel anymore, the distribution shifts back to the left, more negative. And this is because the auger reactors are capital expensive. If you come back to the hearth kiln reactor, which is a less expensive to construct and implement reactor, so claim the authors, then this distribution shifts to the right. And so you can see here in panel D with the hearth kiln, more likely than not, you can make profit from such implementation. Again, this is for the economic conditions back in 2018, which we don't have today in 2021. Fuel prices are much higher today. And so these results I wouldn't take as axiomatic, but what I would take from this is the range of biochar prices quite large, and the range that which other variables play in the system are also quite large, and that contributes to a range of expected profitabilities, net present values in this case. And so this type of analysis is really what's needed to understand the likelihood of a given venture being profitable or not. What this group learned at the end was that though we've been focusing on increasing the biochar yield from these reactors and decreasing feedstock costs, the biochar selling price is the most sensitive variable. And so we really have to better understand what goes into biochar selling prices. So on this slide, we look at the environmental impacts. This is the life cycle assessment slide. And I just have copied here a sensitivity analysis from a paper published out of Argonne National Laboratories some years ago. Note what's not on this figure are the two most sensitive parameters. They are biochar yield and carbon content. They are so sensitive that the other parameters appear insensitive in comparison. So they were taken off the chart. At the top of this chart, we have the soil organic carbon change. And if we increase the soil organic carbon to 0.14 tons per hectare, that's the change. We increase it by 0.14 tons per hectare. We can decrease the greenhouse gas emissions by over 4 grams of CO2 equivalents per megajoule. Okay, and that's kind of interesting. This group looked at biochar application rate, and an interesting thing that they found in the literature was that there are potentially positive priming effects of applying biochar to soils. And so if you add a biochar to the soil, you might actually positively prime microorganisms to degrade neighboring or accessible soil organic carbon. And so adding biochar might not necessarily be a good thing in all cases. They took a worst case scenario to this and subjected this to a worst case scenario evaluation. And so if you apply a large amount of biochar to the soil, they found that there was some evidence of positive priming that could result in increased emissions, but probably not that much. And that's what this blue bar here shows you. If you vary the carbon stability factor, which has to do with how stable the biochar carbon is, 0.8 is the base case value at 0. If you increase that to 0.9, meaning 90% or so of the biochar carbon is stable, then what happens is you decrease the amount of emissions as a result. And so they also looked at nitrous oxide emissions reductions. If you can get a 20% nitrous oxide emission reduction, that also serves to decrease net greenhouse gas emissions. And so this type of sensitivity analysis is important for understanding what most evidently affects the life cycle greenhouse gas emissions response when it comes to biochar application. And so these types of sensitivity analyses are important to perform. It gives you an idea as to what the most sensitive parameters are and what we should be most careful of when we implement these sorts of technologies. That is land applying biochar. So we've learned a number of things. Just in summary, biochar can serve as a solid fuel, a soil amendment, a high surface area absorbent, and many other end uses. Many slow pyrolysis configurations exist, from high tech to low tech, from high cost to low cost. Some you can control, some you can't control. Fast pyrolysis also makes biochar, though in typically much lower yields, and the properties of that biochar are substantially different. Selling prices vary over a large range and are end-use dependent, very least. Production techniques that avoid air emissions and suspended particulates should be developed and encouraged. And biomass fast pyrolysis with biochar land application can potentially produce carbon-negative hydrocarbon fuels. We've learned this from my research at Michigan State. And so if we use fast pyrolysis wisely and upgrade the resultant bio-oil appropriately, we can devise systems that can produce liquid fuel in a way that actually net sequesters CO2. And so I just end with this picture of biochar taken by our own Dr. Jessica Meisel in her laboratory, and you can see its very porous nature. For this reason, you'd expect it to have high surface area. And so lots of applications are dependent on high surface area. With that, I welcome any questions. Thank you for attending.
Great. If there are any questions, I think we can take them. Looks like there's some questions in the chat that are popping up. Should I start from the top, Brooke, do you think, or would it be best to start at the bottom here?
Whatever way you would like to take them. There's also one there that's in the questions and answer forum also.
Oh, okay, great. Oh, thanks for pointing that out. So we'll start at the top. And so it says here, any data on using biochar on lake shores? So I suspect what you're suggesting is maybe these applications where you see putting biochar in these sleeves or socks, and then using the biochar packed in such a way to treat nutrients or unwanted metals along shorelines. That I've heard of. I've heard of doing that with rivers that are contaminated, for example, with things like PFAS. And so there's precedent for those sorts of applications, if that's where the question is headed. If you're talking something else like just blending the biochar into the lake shore itself, I don't know that I'm aware of that. Maybe one of the soil scientists would be able to pick up with that one.
That questioner added something after that. This was in an attempt to filter stormwater runoff.
Oh, yes, there we go. So that's what it would be. Yes, and so you could certainly do that sort of thing. I'll point out that not all biochars are created equally, and I hope to portray that in the presentation. Some have high surface areas, some biochars have low surface areas, some have a high cation exchange capacity, some don't. And so one has to understand the physical, or at least have measured the physical chemical properties of your biochars before applying them. Biochar is certainly not just one thing. It depends on the feedstock. It depends on where the feedstock was grown. It depends on the way the feedstock was processed. So all those sort of steps in the production of biochar, from its cradle, that is the photosynthesis conducted by the plant in whatever environment that plant was growing, all the way to its production as biochar, all those steps matter. So, okay, so that's the first question. Anything to follow up there? It looks like that's pretty good.
In the Q&A.
And so then go to the Q&A next. I do have one question here asking me to define RINs and IRR. I apologize for not doing that. I must have missed those acronyms. You know, some acronyms, when you're so familiar with them, you forget that they actually do in fact need identification. A RIN is a renewable identification number, and this is a program that is established by I believe it's the US EPA, and it allows one to collect credits for producing biofuels. And then IRR is a profitability metric. It's known as the internal rate of return. And the internal rate of return I know is often called the discounted cash flow rate of return as well. It's a profitability metric that accounts for the time value of money. And so it's a little bit more robust as a metric than something simple like the return on investment. The return on investment is just an algebraic relationship, whereas the IRR is a little bit more robust in that it accounts for money's changing values, time value. And so just kind of scrolling through these, there was one on the Kontiki kiln. I believe that was queued up by Brooke. Did anyone have a question there?
It comes up in the Q&A.
It comes up in the Q&A.
They did move their question in there for you.
Oh, so it's moved over there. Okay. Oh, some pros and cons of the Kontiki kiln. Okay. And so the Kontiki kiln is another of these, what I would call relatively low tech biochar production kilns. It would be in the same family as the batch drum kiln that we showed you. But the Kontiki kiln is actually open to the atmosphere. And so you put your biomass inside of it, and then the biomass on the top is what's sort of sacrificed to combustion. And as that combustion takes place, the air that comes around the Kontiki kiln comes in a vertical way. And in so doing, it spreads the flame across the surface of the kiln. And that serves to actually combust volatile organic carbons and particulate matter that's being emitted as the pyrolysis and the combustion is proceeding. And so if you can get complete combustion, ideally you would only emit CO2 and water vapor. And so in that way, such kilns would be a cleaner way of making biochar, cleaner in the sense that the air emissions would be reduced. I'll point out that it's highly unlikely the air emissions are eliminated. It is, after all, open to the environment. And so the efficiency of the combustion of those emissions really matters. Emissions that escape are going to be emissions that one has to account for. That being said, there are certainly lower tech technologies that don't do nearly as good of a job as the Kontiki kilns apparently do. And so that would be an advantage, along with its simplicity and its low cost. And if you go to the web, you'll see these are actually quite easy to cool off. If you have access to a water source, you can just add water. And then when done, you can just dump everything out quite readily. The advantage there versus earth and pit kilns is with the earth and pit kiln, you've got to remove that soil layer that you put on top as a cap. Recognize some of that is going to be hard to separate from your char that you've produced underneath. And you've got to go digging after that char and pull it out of that earth and pit. And so those are some, I think, relatively straightforward advantages and maybe one disadvantage. The disadvantage, again, with the air emissions and to an extent, the yield as well, when compared to the more sophisticated instrumented kilns like the multiple hearth kiln or like the rotating drum kilns or the paddle kiln that we showed you that Cornell has. Those sorts of kilns are going to be able to have really tight temperature control. You're also going to be able to have very tight residence time control. And so the severity of pyrolysis can be very well controlled with the more instrumented kilns.
But if you're looking for a small scale, a Kontiki is an excellent, if you're not looking for a big equipment investment, it's definitely miles better than any kind of kiln situation, earthen setup that you could do in a barrel because of that flame curtain that's going on. And if you're in a country that also needs heat for food production, then you're going to take that to another level of potential there.
And I'll also say, Chris, in your discussion of some of those emissions, that also relates into a question here by David Newman from the Michigan DNR, asking about particular emissions from the continuous production systems that are available today. And I will say just real quick before you answer, we are coming up to 3 o'clock, recognizing that some people might need to be coming off. Anything that's not answered in our follow-up email to today's webinar, where we'll also have a link to the recording, we can answer some of these additional questions, especially those that aren't so much production related I see about water retention and using them in conjunction with mycorrhizal fungi. All very wonderful topics that we can certainly address all of these. I just want to say that with it being 3 o'clock, if we don't get to all of these, they might also be in topics for future webinars for the Great Lakes Biochar Network. So Chris, if you want to say just a little bit more about those emissions and any closing remarks, and we will get all of those other things answered in another way through our website and a follow-up email on this webinar.
Yeah, absolutely. Emissions are very important here. And I wish there were a singular answer, but since there's such a variety of technologies and such a variety of feedstocks, you're going to see a lot of variability with regard to emissions. The constituents that are emitted, their amounts that are emitted, there's going to be variability that we have to account for. The more highly instrumented reactors, this is to David Newman's question at the MDNR, the more highly instrumented reactors, it's actually quite a bit easier to implement downstream pollution abatement equipment, all right, to achieve endpoint emissions that might be desired. That's the advantage of systems that maybe are more medium to large scale, is those technologies become maybe more available and more affordable. At the smaller scale, you know, even with the Kontiki kiln, you're going to have some air emissions. It's not going to be emissions free. So how does it compare as a frame of reference? How does it compare to an outdoor wood stove or a wood-fired commercial boiler system? Wow. Well, it depends on which kiln you're making that comparison to. You know, these earthen pit kilns or the mound kilns, for example, there's quite a bit of emission there. Okay. The Kontiki kiln, those emissions are cut down substantially, but they're not zero. So I don't have numbers that I can compare directly to an outdoor wood stove, recognizing that even outdoor wood stoves have quite a bit of variability.
And again, we can also maybe try to get some more information on those and get some more specifics. Some of those questions about the particulates and everything could go into some of those frequently asked questions that should be coming up on our website. So unfortunately, with the time that we are at, we could maybe stay on and answer a couple more questions, but I wanted to share my screen again just for a second. That's here we are with our future webinars. So much of what Dr. Safran talked about does lead into the economics of biochar production and use. And so hopefully you are available on December 9th at 2 p.m. Eastern time, also to be held here as a Zoom webinar. If you are not already registered, you can go to the link on our website and that will be coming up, and so much more of this will then be discussed in that presentation. And as I said, we can try to answer the rest of these questions through our website and our follow-up email. So thank you all for coming. If anyone would like to stay on, if you are able to stay, Chris, then that is great. But otherwise, we just want to say thank you from the Great Lakes Biochar Network. And again, thanks to our sponsors, Project Green, the Department of Natural Resources, the U.S. Forest Service Department of Agriculture, and MSU Extension. So whoever wants to still stay on with the chat or the questions, otherwise we are going to just keep all of these questions and chat recorded in order to address these further. So thank you so much for coming. Chris, do you have any other last comments?
I think that this technology has a lot of potential. It certainly has a lot of potential to help abate climate change, and there's a lot of other uses of biochar that we're just now exploring. So hopefully this can be a launch pad for looking at those potentialities. So thank you.
All right. Thank you all for coming, and we will hopefully see you at the next one. And keep any suggestions for future events coming to me, glbn@msu.edu. Thanks again.